In response to an invitation from Dr. Felipe Ochoa of the Department of Civil Engineering in the University of Chile, I am presenting this discussion on using rock and rock masses as engineering materials. A brief summary of the basic principles of rock and rock mass strength, followed by a discussion of the application of these principles to a practical example, will be presented. You'll see that there is a lot of text on the slides in this presentation, and this is unusual for me. I normally rely on good illustrations and minimal text for my presentations. However, since you do not have access to some of the basic material that I've used in preparing this presentation, I've decided to include a discussion of this material in some of the slides, and so you'll be able to read this when you have obtained a copy of the video. This illustrates a triaxial cell showing a core specimen with a yellow rubber sleeve to protect it from direct contact with oil, used to apply confining pressures. This cell permits us to obtain a full triaxial stress plot with strain gauge instrumentation for the calculation of deformation modulus if required. The illustration on the left shows two halves of a specimen which was loaded triaxially to about 90% of its uniaxial compressive strength before cutting it in half and polishing the surfaces. Shear failure cracks are visible in the polished faces of the specimen. The Hoek-Brown failure criterion is used to characterize the failure process, and some of you will be familiar with this, with the equation presented here from a reference listed at the bottom of the slide. I'd like to add a note that all my publications and videos are listed and can be downloaded from the Rock Science website given at the bottom of the slide. In my experience, and based on my original training as a mechanical engineer, I prefer to use a lathe for all specimen preparation work in triaxial testing. This includes cutting and grinding of the ends of the specimen, as shown on the left, and cutting profiles of the specimen, as shown on the right. The published triaxial test results for marble are shown in this plot, with the Hoek-Brown failure criterion fitted to the central portion up to a transition from brittle to ductile failure. The tensile tests, based on the use of dog bone-shaped specimens on the left, are shown with a red line fit to the generalized Fairhouse-Griffith plot. This tensile cutoff is applicable to all intact rock specimens without inherent weakness planes. For rock masses, I generally consider that the tensile strength is 0. This table gives a summary of published values of the deformation modulus E, the uniaxial compressive strength sigma Ci, and the Hoek-Brown constant Mi for a wide range of rocks. This table was prepared by Dr. Trevor Carter, a former colleague of mine when we both worked for Golder Associates, and we have found it to be very useful during the early stages of projects where very little test data is available. I've highlighted the row referring to marble, and you'll see that the average values are E equals 77 GPa, sigma Ci equals 90 MPa, and Mi equals 9. From the results on the previous slide of this plot, you'll have been prepared for a range of different intact rocks and different Mi values. Note that the Hoek-Brown curve has been projected backwards into the tensile region to the intersection with the tensile cutoff. This does not provide as good a fit as the generalized Fairhouse-Griffith plot shown on an earlier slide, but it is very close, and it's a good approximation, which is adequate for most design work in rock engineering. The Hoek-Brown criteria for intact rock can be extended to rock masses by generalizing it as shown on this slide. The constants MB, S, and A can be varied to accommodate discontinuities such as joints and blast damage. The Geological Strength Index, GSI, was introduced by Hoek and Marinos in 2000 to provide a basis for incorporating jointing and disturbance into the Hook-Brown criterion. Note that this interpretation of GSI can only be applied to a heavily jointed rock mass, which can be treated as an equivalent to a homogeneous soil. An example of the use of GSI in a very large open-pit mine will be given later in this lecture. This slide shows examples of GSI in different rock masses, and it's very largely self-explanatory. This slide illustrates the Chuquicamata open-pit copper mine in 2013 at the beginning of a transition from open-pit to underground block caving, which was implemented in 2019. I was invited to act as a consultant to the Chuquicamata mine in 1991, and together with Dr. John Reed, an Australian engineering geologist, we laid out a program for testing and data collection for the geotechnical group of the mine. This program was implemented over many years and resulted in a large and reliable database summarized on this slide. The geotechnical database assembled between 1994 and 2012 by the geotechnical team on the Chuquicamata mine is presented here. Note that the footnote in red summarizing the quantity of bench mapping and core drilling is very impressive. The data collection process was very expensive, but it is consistent with the magnitude of the design process for slopes and underground works of one of the world's largest mines. The following slides illustrate the design process for the crusher transfer station in the east wall of the Chuquicamata open pit. About 130,000 tons per day of ore was loaded from the M1 crusher on the pit floor onto the twin conveyor belts in the M1 tunnel. This ore was transferred onto twin belts in the K1 tunnel in the transfer station shown by the large red arrow on the top of the slide. This ore was then delivered into the E4 crusher and then onto the stockpile for processing. In the 1990s, Chuquicamata produced up to 650,000 metric tons of refined copper and 13,500 metric tons of molybdenum annually. In 2018, it was transformed into an underground block caving operation with an anticipated annual production of 366,000 tons of copper and 18,000 tons of molybdenum. The underground crusher station was crucial to the Chuquicamata open pit mining operation, and details are presented in this slide. The cavern itself is a very simple underground cavern with two tunnels for entry and exit of the conveyors. Minor stabilities with one end of the cavern were experienced, and a detailed analysis was carried out to provide any additional support to ensure that such problems did not occur again during the remaining years of operation. The approximate location of the transfer station access tunnel in the east wall of the open pit is illustrated in this slide. This table presents details of the rock types used in the analysis of the transfer station in the east wall. Plots of the Fortuna granodiorite and brecciated sandstones included in the analysis of the transfer chamber are shown here. The mining-induced deformations of the east wall of the open pit and transfer chamber were analyzed using a three-dimensional discrete element model carried out by Pedro Verona, representing Itasca, and Felipe Duran, a member of the Chuquicamata Geotechnical Department. I was responsible for monitoring this analysis and assuring that the critical issues were addressed. The Fortuna granodiorite rock mass in this 200-meter high section of the east wall was incorporated as a homogeneous rock mass. the very important structures shown in blue were included as planes in this model. Details of the three-dimensional discrete element model are shown in these slides. A comparison between the computed and measured horizontal displacements in the rock mass surrounding the conveyor transfer station is illustrated here and shows that the analysis was representative and realistic of the actual conditions encountered in the field. Displacement measurements in the Chuquicamata open pit were carried out using 1,000 prisms and a number of remotely controlled theodolites, as shown here. Measured displacements were telemetered to a central monitoring station for interpretation. Radar units were used for measurement on specific rock elements of interest, but without installed prisms. These units can measure millimeter movements at a distance of up to 3 kilometers. Results of the numerical analysis of the transfer station showing displacements in the surrounding rock mass are presented on the left. This analysis permitted the designers to determine what additional support using tension-grouted cables was necessary in order to ensure that no instability problems could occur during the remaining life of the transfer station. The waste ore from the open pit mine, which at the time of this photograph was about 900 meters deep, was transported to surface in 400-ton trucks, as shown in this slide. This slide shows 400-ton trucks hauling a total of up to 370,000 tons of waste rock per day from the base of the open pit. This 11-kilometer drive required about 2 hours, and as you can imagine, the cost of this process is very high. In fact, the very high cost of transportation of open pit mine waste and ore from the bottom to the surface is a very important factor in the decision to convert the mine from an underground to a block caving operation. The block caving operation in Chuquicamata is still very young, and I do not have any details to present to you. However, this is a good illustration of the Palabora mine in South Africa from an analysis carried out by Dr. Brianne Sainsbury in Australia. And it illustrates the development of the block cave from an underground extraction level and gradual convergence with the open pit behavior and the creation, in the case of Palabora, of a large slide in the open pit. What is important in looking at this analysis is to avoid contamination of the ore with waste from the open pit mine, and this requires very careful planning of the sequencing of different levels of open pit, of underground block cave mining. This is a look into the future and demonstrates the development of extremely powerful analyses which will be used in the future for block caving studies and the design of the interaction between these and overlying open pit mines. Thank you for your attention.